Hello, everybody. Good morning. Thanks for joining us. We're going to be doing our latest episode of some Rosalind challenges today. If you're here, please feel free to say hi in the chat. Let us know where you're coming to us from if you're new. Typically how this works is just a refresher is that we have starter code and completed code links to those in the description of the video. So if you would like to follow along, you're more than welcome to. And that's the natural way to do so. Otherwise, I'll just walk through these solutions to our Rosalind questions, and we're over halfway through them. So today we're going to be talking about some evolutionary challenges around, or some computational challenges around evolutionary trees. And we've introduced trees a little bit in a previous stream, and here's an opportunity for us to talk about some aspects of once we have a tree, what are the types of questions that we're actually trying to solve. And we're going to touch base on this, what we mean by characters and reproducing trees from characters, a very old school idea that actually is still relevant because of how we think about genetic data these days, but more on that shortly. The other thing that we're going to see quite a bit in this particular stream is breadth first search. So there are essentially two classic ways of exploring a network or a tree. Depending on the particular application that you need, one of those is to start at a node and try to explore as far into the network as you possibly can. And then when you reach something, come back, some amount, and then continue to try and explore deeply into the tree. So that's called depth first search. And the other approach, which we're going to see today, is called breadth first search. We've actually kind of introduced this a little bit in a previous stream when we looked at a question about rearrangements, but it was in a completely different context. Breadth first search says, essentially, I might have 10 different nodes that I'm connected to. I want to try and consult all of them. And then for each of them, I want to consult all of their neighbors. This is a great application whenever we want to have, we're looking for like the shortest path between two nodes. And in the case of trees, as I'm going to say today, there is the path between two nodes is always going to be unique. And so for that reason, if we're trying to find the shortest path between two nodes, it's really the same as just finding a path between two nodes. So more on that momentarily, but that's going to be, we're going to essentially implement breadth first search in like 3 different problems that arises in slightly different contexts. We're also going to talk about formats for how trees are stored. Like if I have a notion of an evolutionary tree, I know that I'm connecting orangutans over here and chimps over here and llamas and us and bacteria and whatever I'm putting into the tree. And all of the leaves of that tree are called taxa. So they could be individuals, they could represent species, they could represent a genus, so whatever level that we're representing at the leaves of that tree. It would be nice to have a file format that we can say, you draw the same tree that I do. Well, we can exchange the information contained in that tree in one single agreed upon file format that we have. So we're going to talk about Newick format a little bit today as one of these file formats that we can agree upon to standardize how we're going to represent a tree. So that's what's on tap for today. We're going to look at 6 questions, and they're all around evolutionary trees in some form or fashion. They'll build on each other a little bit, as we're going to see. And I think we're nearly ready to get started. So as always, I will usually go through each of these questions, and the questions that we're going to consider are going to be in the description of this video alongside the starter code and the completed code that you need. And then I'll happily answer any questions that you have live between questions. So feel free to just put those in the chat, or if you have any other comments that you want to make, that's great. It'd be great to hear from you. So we're going to get started. Our first question is going to be NWCK. In the meantime, I would just say we had a big week with Philomath this week. We had our close of Programming for Lovers in Python. So we did some assembly language and we traveled to the dark heart of computer science. So if you hadn't had a chance to watch that video, we polished everything up, and now everything that we did with that course is we're still adding a little bit of content to the website, but the course is going to become stable, asynchronous. It's going to live permanently in a place that if you want what I think is the best course in how to learn Python, if you're interested in science in the world, it's going to be completely free. Check that out at programmingforlovers.com. And then in our pinned comment here, as well as in the description, there's a link to join Philomath. And if you're interested in that, especially because we have kind of in 3.5 weeks in late June, we have our Vibe Coding Studio course, which we put out a trailer or a little introduction video for earlier this week. So please take a look at that if you haven't had a chance to look at that already. We're going to have a short course where I cover a few lectures for about 4 weeks and just show you how to go from like 0 to something with vibe coding and appreciate kind of where are we at the, like, what's the state of the art for how I would come to trying to tackle creating a portfolio project where I feel like I've learned something, but I also feel like I've been able to build something in record time that I also know is correct. So we're going to learn a little bit about the foundations of AI, take that up towards like practical uses of AI. Like what are the tools that are out there? What are they good at? How can I effectively use them? And then show how to educate yourself using AI tools as well. So like once I have something that I'm particularly interested in, how can I still provide human learning there, but use the AI tools to help me grow my brain bigger and faster? And then once I do that, how is it that I take all that knowledge that I have alongside the fact that I now have a second brain to help me build something and make sure that I am managing that second brain effectively to make something that I can then put my stamp on and say, hey, I made this thing, and it would have taken me literally months probably to build something like this previously, but I can probably just do it in a few hours a week here and there as a fun project and still have something I can put my name on at the end. So that's what's thrilling about this era, that everything here, like there's ways of learning things in different ways. Are we going to completely abandon anybody ever learning how to program? Probably not. Like there's extreme value in learning how to solve problems computationally and understand, like if you didn't know what BFS is, you're not ultimately going to make it very far in computer science these days. So there's still value in appreciating it. But we also have these immensely powerful tools. And that's the purpose of our mini course, is to kind of explain to you how they work and make sure that you're using them effectively. Because a lot of times what I see with our students, even at like an elite computer science institution, is they're not really appreciating the power that they've been handed, and they're not necessarily taught to wield it appropriately. And that's what I want this course to be about, because what AI can do for you is so much more than firing up a chat bot and asking it to help you make pasta salad. So that's it for that. Again, if you're interested in our Vibe Coding Studio, it starts June 22nd. We have some promotional pricing. There's like a founding member hall of fame that we're going to have if you sign up before June 1st. So that unlocks a bunch of other stuff, Programming for Lovers ebook, access to our member Discord. There's more stuff coming. We've got great ideas in Comp Bio coming this fall. All that stuff is coming soon. But for now, I think we're ready to get started. So as I said, we are going to look at NWCK first. As always, let us know if you have any questions in the chat. Like and subscribe, drop us a comment, all that good stuff. And we're going to start. So NWCK is what we'll look at first. I just added a breakpoint. Let's not do that. And let's code. NWCK is distances in trees. And if you've followed along previously, you might remember what a tree is. So fortunately, mathematics gives us rigorous, concrete definitions of concepts like trees. And in this particular case, a tree is a network, but it also has two critical properties. So a tree has to be connected, meaning it has to be possible if I walk along edges between pairs of nodes. I have to be able to reach any node from any other node. The tree also has to be acyclic, meaning it's not possible for me to walk from a node through to a path of some other nodes and then ever return back to where I started. So those two properties are a little bit conflicting. The connectedness wants to add edges into the tree, and the acyclic aspect of the definition wants to remove them. And as a result, whatever our trees look like, I just have 3 little trees for us. Whatever our trees look like, in either of these cases, you can see that they're connected. Pick your favorite 2 nodes. It's possible to reach one from another. You can also see that they're acyclic. So regardless of what these like constellations look like, it's not possible to start at a node and travel to other nodes and come back to where you are. But they wind up taking different shapes. Yet what we saw in a previous problem was that regardless of what shape they have, these two forces of trying to add edges with connectedness and subtract them with this acyclic condition produces an invariant. And the invariant is a mathematical theorem that if a tree has n total nodes, it always has n minus 1 total edges. This is an idea that we're going to come back to. But for now, I will say that we're interested in representing a tree in a way that can be exchanged from one program to another. And so we need a file format in order to do that. And one classic way of doing that is called Newick format. It's named after a seafood restaurant in New Hampshire, of all places. And I don't think they're the most thrilled about the fact that an evolutionary tree file format is named after their establishment. I don't think that there's like a big statue of an evolutionary tree out front, and I think there should be, frankly, but that's their own decision. The way Newick format works, though, is with parentheses. So it establishes that if you have 2 nodes that are neighbors, and here's a tree over here on the right where C and D are neighbors. What are neighbors? Well, they're leaves of the tree, meaning they have degree 1. They're at the tips of the tree. So we can see that they're only connected to one other node. But there's a little extra to them, which is that the one node that they're connected to is shared. So that's called the parent of C and D. So in this tree, C and D are neighbors, and A and B, I suppose, are neighbors too. And the idea of Newick format, then, is to say, well, you can join 2 neighbors together in some fashion. And once I do that, I could parenthesize C and D to say the DC, which you see here, represents the parent of C and D. And so I can parenthesize that in that way. And once I've done that, well, notice then you now have 3 remaining nodes. They actually all are neighbors. So this is the parent of A, B, and this node. And so that is how we produce this Newick format A, comma, D, comma, C in parentheses, comma, B. So A, B, and the parent of D and C are all at the same, they're all neighbors of each other. So the idea of Newick format is to like work from the inside out and progressively parenthesize, I think that's a word, parenthesize our tree into a string. So if you work with Python a lot, that idea is hopefully comfortable to you, that regardless of what kind of structure that you have, we can convert it into a string in order to represent it in some way. And Newick format is just doing that same thing, with the caveat that there's multiple ways of doing this. So I also could have joined A and B together. And if I join A and B together first, well, that's the parent of A and B. So I would have the parentheses A and B together. And I could have also, I suppose, represented it, them first. But then once I've got the parent of A and B, it's a neighbor of C and D because they all share this node that they're connected to. So that would give you this particular representation. So the representation isn't necessarily unique. There's multiple ways possibly of representing the same tree. But if you give me a representation, I know that it can only correspond to one tree, which is nice because if you generated this tree from an algorithm and I want to visualize it in a different program, well, you just hand this tree to me in Newick format and then I can make it. There's an unrooted version of this. I wanted to show you, the platform doesn't have it, but there's also like a rooted version of this. So in this particular tree, E is the root. So everything flows outward from the root. And as a result, well, we might say C and D are neighbors. So you see D, C here connects those two. And then once we're at this level, A, this parent node of C and D and B are all at the same, like, they're all neighbors of the root node E. So we would want to represent the tree in this way. And then there's one separate thing, which is that previously we might not have been labeling this node, but now that we have a labeled root node, the labeled root node just has its label at the end of all these parentheses. So as a result, we can represent rooted trees, or we can represent unrooted trees. And this gives us questions around this, which is, well, say for example, we were given a tree in Newick format. Can we answer questions about that tree itself? And here's a very straightforward question, which is, I might have a tree and the platform is going to give us n trees. But if I have any one tree, I'm going to do this n times. I have one tree and a pair of nodes in it. And I want to say, what's the distance, meaning what's the number of edges between those two nodes in that particular tree? So by representing the tree in Newick format, it makes it much cleaner to kind of send you a tree. So here's the Newick format in a pair of organisms, and here's a Newick format in a pair of organisms. Instead of saying, well, how else would we get to you the data that you're interested in here, which is a tree? Now we have Newick format. We can send you the data as a sample or as a larger data set on the Rosalind platform. There's something else that's lurking here, which is, well, a couple things before we solve the problem. Number one is there is a consequence of the fact that trees are connected and acyclic. Because they're connected, there has to be a path between any two nodes. But because the tree is acyclic, it means that the path has to be unique. So pick your favorite two nodes in any of these trees. What you'll notice is, if I pick, say, this node and this node, well, there's a unique path of edges connecting them. There's only one way of getting from that node to the other. A natural way of seeing this and how you would prove it mathematically would be to proceed by contradiction. So assume that for some reason there are two nodes that have two different paths connecting them. And you could imagine, well, I could go one direction and I could go another direction. And that means that somewhere along the line, I must be forming a cycle. And that can't be the case because, well, we know that a tree is an acyclic network. The other thing I want to point out is the platform is trying to get you a little bit comfortable with appreciating that this is our Newick format of a rooted tree, and this is the Newick format of an unrooted tree. So I'll show the difference between those two trees. The first one is rooted, which means that cat is on its own as a leaf, and it's connected to the root, which is dog. So the idea is that time is flowing from dog to cat. Now, this isn't necessarily true biologically, but it's what this particular sample is representing. So this would be saying that dog is the ancestor of cat. Probably the cleaner, more correct biological conclusion is not that cats have evolved from dogs, but that they share an ancestor. So if we instead represent the tree in this Newick format, we're saying dog and cat are neighbors. We're not labeling the root node connecting them, which is their ancestor. So we would just have parentheses around dog and cat, and then the semicolon indicates the end of the tree. So in this tree, the distance between dog and cat is just 1. In this tree, the distance is 2. And that's what the sample output is getting at here, to say we have the rooted tree, the distance is 1, the unrooted tree, the distance is 2. And so the output is trying to get us to see that these are in fact different trees, so the distance between them should be different. It should be 1 here, and it should be 2 there. Now that we understand what it is that we're actually solving, the idea becomes, well, how is it that I can take that and actually find the distance between two nodes in a tree? That's really what this question is asking. And unfortunately, there's a separate part of this question, which is that when you're given the data, the first thing you need to do is learn how to take a file that's in Newick format, take this string representation of a tree, and convert it into something that's a lot easier to work with. I could, of course, spend time on stream discussing the parsing of this, and I feel like that would be time that's immensely wasted. It's more interesting to go from a tree to its Newick format, because it's like just a beautiful recursive algorithm. We'll save that for another day. It is extremely boring to go from Newick format to conversion into a tree. So that for that reason, everything's going to be provided in our custom io.py file for doing that, and you can investigate it if you like. I'm far more interested in, once I have a tree, starting at the node that I care about. So in this case, it would be dog. How is it that I can get to cat? And here's where breadth first search is going to be very useful, because from the dog, I'm going to explore all of its neighbors. And it's a leaf node in a tree, so it's only going to have one neighbor. But once I start going into the tree, I might start seeing some branching. And so I'll have one neighbor from dog, and then it may have a bunch of different neighbors of it. And so I'll explore all of those. And then from each of those, I want to continue exploring. So what I want to keep track of is, have I seen a node yet? Because as I explore the tree, and we're fortunate because the tree, it's acyclic, I know every time I explore out from a node, I have not seen the node that I'm going to see, unless I'm going backwards in the tree. So I do want to kind of keep track of the nodes that I visited, and every time I encounter a new node from the neighbor that I'm at, exploring all of its neighbors, I'm going to say, have I seen it before? And if I haven't seen it before, I need to update to say, how far is it from my original node? So it's going to be a nice, simple implementation of BFS. But before we even get there, we probably also need to establish, well, what is it how is it that a tree is going to be represented? So this is our first instance of needing something in data types.py. And the first thing that we're going to need is an user-defined class called a tree. And it's not going to actually have much associated with it. So the tree is really just going to contain one attribute. And so this is our init method that will initialize a given tree. And its one attribute is going to be what we think of as an adjacency list. So all of the nodes of the tree are going to be represented as strings. We're not going to have a separate node attribute or class. What we are going to do is represent the tree as its collection of edges. And so those edges, how can you represent that? Well, what the adjacency list will tell you is, for a given node, what are the other things that it's connected to? This is going to be a little bit redundant because, well, if I'm at this node, I will store, all of the edges that I'm connected to. And so say I'm connected to node A. When I'm at node A, it's going to store the connection back. So every edge is going to get stored twice, but this is going to be a nice, clean implementation otherwise. And so we'll have a dictionary that maps strings, which are our nodes, to all the things that they're connected to. So everything that they're connected to would be a list of strings. So those are all the other nodes, but we're going to add one other thing to it that's going to be useful in a future question, which is, when I'm connected to another node, I want to also store the edge weight along that. And that's very useful in the context of evolutionary tree construction, because two taxa or two nodes in the tree might be very close to each other, or they might be very far apart. So all the edges benefit from having a weight. And that's where we get that it's not a list of strings, it's a list of these tuples, where the tuple contains two things. It contains the string, so the node that this particular node is connected to, and then the float represents the edge weight along the way. We also have a few methods that I went ahead and wrote for us, because these methods are going to be useful and they're not particularly complicated. Like, for example, if I have a tree and a current string, meaning a current node, what are the edges that it's connected to? So what are the different possible neighbors that I can reach? That's just a matter of going in and accessing, for me, what is in the adjacency dictionary, what is the value associated with my key? And that's this list of tuple of strings of floats. And then we have simple functions like, am I a leaf? Well, when I look at the number of neighbors, which is this thing, does that have length equal to 1? If it does, return true. If it doesn't, return false. We have a has method that says, well, is this particular string, is it a node of the tree? And, well, it's a node of the tree if it's in the dictionary as a key. So if it is, this will return true. If it's not, it's going to return false. And then we have leaves and edges. So go through and find all of the leaves of the tree, meaning the things that have degree 1, all the things that are at the tips of the tree. And how do we do that? Well, range over the dictionary, representing all of these edges or adjacencies. And every time you encounter something that is a leaf, I could have just as easily have called isLeaf here. So if this is a leaf, append it to a list, and at the end return that, possibly sorted. And finally, what are the collection of edges in the tree? The only thing you have to do here is to acknowledge that every edge is currently stored twice. The adjacency list stores A to B, but it also stores B to A. So you just need to range through and take only one of those two things. And that's what this tree does. It uses a set in order to do it. So the set automatically removes duplicates. And in particular, it uses this frozen set, which is an immutable version of the set so that it could be used in places where you need immutable things. But that's a minor point. Once we have that, I think we're ready to write our solution. So we really want to spend time on what we care about, which is our implementation of breadth first search. And there's a minor point here, which is before I can even do that, this particular question is going to give me n different data sets. So I'm calling that queries. And each query, so it's a list of things, each query is 3 things. It's a tuple containing the tree itself, and then the 2 nodes that I want to connect in that tree. At the end of the day, for each such tree and each such pair, I just want an integer, which is the distance between them. And so I'm going to wind up with just a list of integers. When we look at our Rosalind platform, we see each tree gives me, each data set gives me a tree and a pair of strings, a tree and a pair of strings. And at the end of the day, I want to return a list of integers corresponding to the connections between them. Pretty good. So in this case, I have a list of things. This is a very natural thing to do, which is to range over the list and call a subroutine that we care about. So at the end of the day, the answers that we want are going to be a list of integers, and that's what we'll eventually return. And in the meantime, I want to range over everything that's in that queries data set. So in the queries, we're going to get a tree, we're going to get name A, or we're going to get name B. And as I range through it, we want to say append to answers the result of counting the number of edges on the path, which I'm going to call path edge count as a subroutine, of the tree for the 2 strings. And that's all this function is going to do. Classic thing in programming where you want to do something n times, so you just have a for loop to do it, and then you call a subroutine to do it once. And that's the subroutine, of course, that I really am interested in, which is path edge count. So it takes a tree, takes a start node and an end node, and it tells me the number of edges on the unique path between those 2 nodes of the tree. Remember, that path has to be unique because the tree is acyclic. So if you had 2 paths between 2 nodes, you'd form a cycle. And here's where the BFS will come in. So we can implement this subroutine first by performing some simple checks. So, like for example, if the start node is equal to the end node, well, we know that the distance between them is 0, so we need to handle that case. And another thing would be, well, make sure that these nodes are in the tree, because somebody could break this by saying, well, let's give it a start or an end node that's not actually a node in the tree. So I'll check to say if it's not the case that the tree has the start node, I get to use my method that comes from datatypes.py that we talked about. That takes a tree, it's a tree method, and it takes as input the string, and it says check to see if that string is a node of the tree. So if start is not in the tree or end is not in the tree, in either of those cases, I want to return a special value. I could also have an error message, but I'll have a special value of -1 to flag that they're not in the tree. We've also seen BFS a little bit previously. So there was an implementation that we looked at in rear.py. And in this particular case, you may remember it. This is one of our trickier questions that we've encountered. And the idea of this question was we represented this kind of BFS search where we were looking at permutations and all the ways of changing the permutations in each step. I didn't frame it in this way before, but what we really were doing was exploring a network of sorts where the nodes were permutations and the edges represented these permutation operations. So they represented rearrangements or reversals on the permutations to take me from one permutation to the other. And the idea was I wanted the fastest way of going from one permutation to another. So I was really kind of exploring a network. And in that case, our implementation was tough because we needed this meet in the middle breadth first search. We were growing two balloons. You might remember this. And when the balloons touched, that was when we sort of met in the middle. The problem was if I just explored outward from one place, the balloon was going to get huge and it was going to blow up our runtime. So the trick that we had was start at the start and at the end and meet in the middle. The fortunate thing about the tree is that, remember, the tree is acyclic. So there's only one, we're not going to blow up. There's not that many edges in there. So we're not going to blow up the number of possible paths that we could go from one node to the other. So it will be fine to just start at the start node and then explore outward. So we don't need anything quite so fancy here. But what we do need to do is keep track of the distance to each node. So we'll say, let's do that with a depth dictionary that maps nodes or strings to integers. And it starts off with one thing in it, which is that the distance to the start node is, of course, 0. We're also going to represent breadth first search always comes with a queue. We could get this from a built-in package in Python, but I'm going to show you that we can kind of implement this on our own. So what is a queue? It's basically a list where the list is first in, first out. So meaning as we place elements into the queue, the first thing that goes in is always going to be the first thing that goes out. So if we put 10 items in, the first one to come out is the first one that went in. So it's a nice orderly data structure. And we'll use an index to represent kind of what's the current element in that queue. And I'm going to call that head. So it's going to start at 0. And then we're going to have a while loop that ranges and performs the BFS. So while it's the case that, in this case, our condition is going to be, I don't want the head to ever go over the length of the queue, then I would have a runtime error. So I'll make sure that the current thing that I'm looking at is shorter than the length of the queue. That's good. I'm going to set the current node equal to accessing the queue at whatever the head index is. So that's our, current customer served, so to speak. And every time I'm entering this, I want to move to the next customer. So this is just updating. For the next time through. And now we just range over the current, or the neighbors of the current node. How can I do that? Well, remember that I have tree.neighbors of node. So that's something that's really helpful. That's another method that comes from the tree type or class that we defined. So this gives me a list of strings, which is good. And in that particular case, well, it doesn't give me just the strings. If we look at data types, the neighbors technically gives me the strings, but they also give me the edge weights as well. that I'm using here. And here I'm not actually representing those edge weights because everybody just has kind of this default edge weight of 1. But I need you to remember that the neighbors are going to come out as a list not of strings, but as a list of tuples of strings and floats. I'm not interested in the floats. So when I range, I want to do this and say for the neighbor of the current node in tree.neighbors of node, but technically I get the edge weight too, and I don't care about it so right now, so I'm going to have an underscore there. So that gives me the neighbor and the edge weight. I won't use the edge weight, but what I will say is, have I seen this neighbor before? And in the case of trees, that's relevant because I could be exploring the tree, and then one of the neighbors of each node is the node that I just came from. So I don't want to consider it. What I want to say is the current neighbor in depth or not? So is it a key of this? And this is representing whether or not I've seen that particular node before. So if it's not in the depth, that's good. So now we want to update the depth of this neighbor. And I can do that just by saying the depth of the neighbor is whatever the depth of the current node was plus 1. We ask one more question, which is, are we finished? And I can know that I'm finished if the neighbor is equal to the end node. So if that ever becomes the case, we've kind of hit our final answer and we've reached that node the fastest. So this is why breadth first search is so useful for shortest path types of problems, because the first person to reach, we're expanding out in one wave each time. We're blowing up the balloon kind of with a unit length each time. And so the first person that reaches the target node by virtue of that design of the algorithm is going to have to be the winner. So the first time that I encounter neighbor equal to the end, I'm going to return the depth of that particular neighbor. And that's my answer. In the other case, I'm not returning, so if I'm here, neighbor is a new node encountered that we need to explore. So what do I mean by that? I mean that neighbor needs to go into the queue and we need to add it. If we have reached this point of the code, it would be strange because along the way, we need to have returned something. So if I've ever gone through this process and successively blown up the balloon and considered neighbors of neighbors of neighbors of neighbors, and I never actually reached the end, there's something wrong. And so we have no solution, and we're going to return our -1 default value again. Now, of course, it's just a matter of running this. So we've got our Rosalind folder, and then we're going to say, we can run this on Python 3 NWCK.py, and that gives us 1, 2, which is the sample output that we saw on the platform. So we can go ahead and download a data set, come back to VS Code, and we're going to put that data set into our file explorer, call it dataset.txt. And then as always, we're going to uncomment the part of the code that's going to parse out the larger data set. And I got a list index out of range, so that's not good. So I know how to fix this. Give me 1 second. So in this particular case, this is just making sure that I have the right custom IO. I had updated it, and I don't think it made it into my starter. Let's try that again. Let's try that again. Okay, that worked quite a bit better that time. And now that we have that, I can take my answer, which is here. It's also in the output data set. And we can go to our platform. and submit. We still had all the time in the world there. And we get an answer. And it suggests you should try the next question, which is Newick format with edge weights, which we're going to do. So that'll be our next question. If you have any questions, want to see something again, in the meantime, let me know. All right. Be getting a setup here. Next question is NKEW. All right. Moving on. NKEW is Newick format with edge weights. So we've already talked about Newick format a little bit. And as I mentioned previously, when we look at real evolutionary tree construction, we also often want to have edge weights representing kind of a distance between two nodes in the tree. So if we look at, a tree like dog 42 and cat 33, this is a tree where cat and dog are connected to a root, but the distance from dog to its parent is 42. The distance from cat to its parent is 33. So they're both connected to the root, but we've added to that. I wanted to show you the tree for this larger make-believe evolutionary tree in Newick format, which is if we have this particular data set, we have dog goes to 4 and cat goes to 3. So it's the same type of thing. Dog and cat are connected to their parent with edge weights 4 and 3 respectively. And note that in terms of the parentheses, this parent and the robot and the elephant are all at the same level. So we know that the tree is going to be elephant, robot, and that parent of dog and cat all connected to one node. Note that may or may not be the root of this tree, but it is a node that they're all connected to. So the root could be here, it could be here, it could be on any of these edges. But the parent of dog and cat is connected to that node with edge weight 74. The robot is connected to it with edge weight 98, and the elephant is connected with edge weight 58. So we've not actually added a great deal to this particular Newick format. And the format itself is going to be basically the same. This particular question asks us, what's the distance if you add up the edge weights connecting two nodes in the tree? And here is where, well, for cat and dog, you can see it's going to be 42 plus 33. For the distance between dog and elephant, what you're doing is you're identifying the unique path connecting dog and elephant. So this is inherently connected to the breadth first search approach that we have already seen. But then on top of that, you want to add up the edge weights that you encounter. So 4 plus 74 plus 58 is, I'm going to trust the platform. I have a PhD in math, which you may know means that I'm horrible at arithmetic, but 4 plus 74 plus 58 is, at least in theory, 136. And so all I need to do is, when I perform my breadth first search, I need to add the edge weights into it. That might seem like it's very complicated, but the idea should be very inherently similar to what we've already done. So my goal for this particular question then is to solve this question in as similar a manner as possible to NWCK. If I wind up with one solution for exploring the path between two nodes where all the edge weights are 1, and it's radically different to an approach that explores the path between two nodes with BFS where I have edge weights, then I've done something wrong. And so what I want to do is look at my code that I had before with NWCK and ask myself, is it possible to just take basically the same implementation? So I will still have this same code because the structure of the problem is the same, in that it's going to give me n trees and n pairs of leaf nodes that I want to connect. So I'm still going to have this Newick distances or Newick weighted distances function where I'm going to range over all of my queries, which are tuples of trees and the two nodes that I want to connect. And then I'm going to call this path edge count function, which here is going to be called path weight, because I'm not just counting the edges, I'm actually adding the edge weights that I encounter as I go. At the end of that process, I return the answers. So everything here is the same. That looks good. Then I look at the path weight function that's going to take my tree. It's going to take my start and end node, and then it's going to return a float, not an integer, because, well, the edge weights can be represented as floats. So I'm going to be summing those edge weights, and that's what I want to return on the path between start and end. I'm going to take my code for that, and I'm going to do something a little bit dangerous, which is to copy the whole thing over, but it's not too dangerous in this particular instance because, as I said, I know that the code should be basically identical. And if it's not, well, there's a problem. So I go through my checks first and say, is start equal to end? If so, I return 0. So there are no edge weights connecting a node to itself. And then I say, are the two nodes in the tree? That also seems important. I'll return this value of -1, or I could produce an error. I want to keep track of the distance to each node. That's a good thing to do, except I'll probably want to add something to it. And, I'm going to make this a float and this a float. And that means that I probably should make this a float also. And this is not going to be a dictionary mapping strings or nodes to integers. It's going to map them to floats. So I'm just making appropriate changes as I go. The queue is still going to be the same. It's going to be a list of strings that starts out with the start. The index of what I'm looking at in the queue is going to be the same. My invariant here of checking head is less than the length of the queue to make sure I don't overshoot the queue somehow is going to be the same. I'm serving the next customer and then I'm updating. All that's the same. And I'm doing breadth first search, so I'm still going to range over the neighbors of the current node. Except that in this particular case, and you know what, I'm also going to, calling this depth actually is a little bit suboptimal. I'm going to call this weight so far. Okay, that might be a little bit more descriptive. So I'm not counting the depth, meaning number of edges. I'm also keeping track of the edge weights. But everything else kind of up to this point is the same. The only difference is now when I call tree.neighbors of node, I remembered that gives me the neighbor, but it also gives me the edge weight. And the edge weight that it connects to is actually important. So I want to say edge weight is going to be here. It's not colored in light blue yet because I haven't used it. So I do need to use it. And I want to change any occurrence of depth with weight so far. So I'm going to do that here, and here, and here, and here. Okay. But I will still say, have I seen this neighbor before? This will be the same check. Is it a key of the dictionary? If I haven't, then I want to update it. And before I was just adding 1 to the depth value associated with the node. So I was adding kind of 1 step away from the depth of node. Now that 1 but changes a little bit. That's where our edge weight comes into play. So the edge weight really matters, but otherwise this line of code structurally is the same. We're still going to say, am I done? So anytime I reach the end, I'm finished. And I will return, and what's nice about this is I know I have a tree. So there's only one way of reaching the end. You might be worried because before I said, well, the first time you reach a node, you know that the end node, you know that that's the best way because I'm blowing up the balloon. But note, for a tree, if I reach the end, I know I'm on the unique path connecting start to end. So that's an important point. And once I reach the end, I can safely return the weight so far of the neighbor. And then, of course, if I'm here, neighbor is new, and I append it to the queue, so it takes its place in the line. And if I reach here, I have no solution. So I achieved my goal, which is I wanted to change my code very little. And I just changed the dictionary to have, values that are floats instead of integers. And every time I want to update that particular weight, I add the edge weight instead of adding 1. Otherwise, the code is going to be the same. So we'll run it on our sample data. 75 and 152 that we had before. That's what's expected. Okay, so we have a slightly different sample data set here. I probably should have had the same one from the platform. Oh well. And we're going to download the data set. And we're going to add that data set into our file explorer, call it dataset.txt. Comment out or uncomment out the parsing. And we're going to run it. We get an answer and output. Put that back in the platform. We should get an answer. Hooray. Let me know if you have any questions. We're going to move to the next one, which is CTBL. CTBL is creating a character table. This problem is all about making phylogenies or evolutionary trees from what we call characters. And the classic definition of a character is an anatomical or physiological property. So if you're working in the 19th century in biology, for example, you're likely really studying visible organisms. Not necessarily, but this is a huge proportion of biology. And you're dividing them based off of things like the fossil record, which are the data sets that you have access to. A notable example would be Harry Seeley's division of dinosaurs into 2 main categories, Sauriscia and Ornithischia, based off of hip bone shape. He made an amazing observation that regardless of whether dinosaurs were carnivores or herbivores or flying or swimming or wherever it was that they were, the largest division between them appeared to be that some dinosaurs had a hip bone that was like a lizard, and some dinosaurs had an inverted hip bone that's like how birds have their hip bones. And that's neat because, well, we are never going to have like DNA data from dinosaurs, but we do have the fossil record, and that so the underlying data hasn't changed, and so that evolutionary tree, that main division of dinosaurs, hasn't changed since then either. These days, there are still characters, very much characters, and we'll see this in a future question. But the characters become based off of genetic or genomic data. So, for example, if we're comparing modern day species that all share the same gene, and this gene might be hundreds or thousands of letters long, whether we're at the DNA level or the amino acid level, and we can create a multiple alignment of all those things. Well, each column of that multiple alignment that says, does this organism have an A or a T, for example, at this particular position of that alignment? That in and of itself is also a character because it's like a little light that switches on. Instead of this being the shape of the hip bone being in one of the two categories, it's, well, does this organism have an A or a T, or possibly other letters? But you get my point at this position. Mathematically, we've also started looking at sets on the platform. So everything here is framed in this set theoretic notation. But we can get to use them because if I have the character, I possess an A at this position, or I have a lizard hip bone shape, I might say, well, the light is on and I'm going to add this organism or this taxon into set S. And if I don't, I'm going into another set that's complementary to it that I'm going to call SC, which is just the set of all taxa that don't have the character. So where the light is off. And if there are two options for each character, so the hip bone shape, for example, is binary, or this position of the gene is either an A or a T. If that's the case, well, I can encode all those as ones and zeros when it comes time to produce a table of characters. The idea is that this character table here corresponds to the tree. So each row is a character, and this is saying that whatever these organisms are, the first two do not contain it, or the light is off. These two, the light is on, and these two, the light is off. One thing I'll point out is you can switch the ones and the zeros, and it doesn't really matter. All that matters here is I'm dividing all of the organisms behind the scenes into two categories. Same thing here. This is saying these two organisms don't have the light on, and these three do. And so from that perspective, what these characters should do is divide the organisms in the tree. So if these three organisms share this and these two don't, well, there should be an edge of the tree where all of the three that have this character are on one side and everybody on the other side don't have them. And so this is called, in evolutionary tree studies, this concept is called a split because it means there is some position in the tree that divides all the taxa into two camps. And that makes sense. Imagine you were drawing the dinosaur tree. You might draw an edge, and then you would have two nodes, and one side was the lizard hip bones, and the other side was the bird hip bones. And then the tree would expand outward from each of those positions, but that edge would kind of split the data. So if we come back and we look at our, here is the Newick format. The input is going to be an unrooted binary tree in Newick format. And binary tree just means, an unrooted binary tree means every internal node has a connection to exactly three edges. So every time I enter a node, there's two things that leave it. And we're going to say a little bit more about that shortly. But here is the unrooted binary tree that corresponds to this Newick format from the sample data set. So you can see we have elephant and mouse, our neighbors, and they're at the same level as robot. So its parent is connected to robot. And then dog, cat, and robot, and that parent are all connected to the same node here. So if we have this, you'll notice there are two edges of interest here. An edge like this one is extremely boring because you'd say, well, what is the split that it corresponds to? It puts the dog on one side of the tree and all the other organisms on the other. So there's nothing interesting there, right? everybody is going to get connected to some node on their own. So this node is not interesting, this one, or this edge is not interesting, this edge is not interesting, this edge is not interesting, and this edge is not interesting. There are only 2 edges in the tree that actually correspond to anything of interest in terms of splitting the organisms. It would be this edge here connecting the parent of elephant and mouse to the parent of robot, and it would be this other edge here. So what makes those edges special is they don't connect to leaves. They're what we call, the technical term would be an internal edge, because it connects to internal nodes of the tree, not touching any leaf. And so there are 2 splits. There is this split of the data and this split of the data. So if we look at this split of the data, it says dog and cat are on one side, and robot, mouse, and elephant are on the other side. And this split says elephant and mouse are on one side, and the other 3 organisms are on the other side. So think about a split as if you removed this edge, you would wind up with 2 separate trees. What are the taxa in tree 1 and tree 2? All this can be represented again in terms of the light switching on and off. If I agree upon an order of the taxa, a natural order would be, let's sort these things lexicographically. So you'd have cat first, then dog, then elephant, then mouse, and then robot. And if you look at an edge like this, now when we go back to the platform, bring that back. We go back to the platform and look at the first row. This is cat, dog, elephant, mouse, robot. This is like a memory test. So cat, dog, mouse, cat, dog, elephant, mouse, robot. It's harder than it seems. And this is cat and dog. This is elephant and mouse. And so the 2 ones here correspond here. So this row of the character table corresponds to this edge. This edge says this is this particular row, because this is elephant, mouse, and robot. Those are the final 3 elements. So this edge says elephant, mouse, and robot would be in the tree over here, and cat and dog are over here. So they're getting those 2 zeros. So the idea is we're going to take a Newick format of a tree, form that tree, range through the tree, identify all of its internal edges, and then say for each internal edge, what's on this side of the tree and what's on the other side of the tree, and use that to form this character table that represents, this is what, for this tree, this is what this tree divides out for each particular edge. These are the splits. And so we're able to kind of understand, without necessarily looking at the tree, this is telling us that there's some edge that divides out elephant and mouse, and another one over here that divides out cat and dog. And that's a useful data set because it's so concise, right? It's just this binary matrix. And we're going to look at a couple problems here that involve it. All right. So we're going to come to the coding side of things. And what we would like to do is, for a given tree, we'll let our Newick parsing handle everything here. We want to return a list of strings, and the strings are just 0, 1 strings. So each string is going to be 1 row of this particular table. It's not going to be a hard question, but it will be a little lengthy because we've got to take the tree, we've read in the tree, that's its own step. And once we have the tree, I've got to find all the internal edges. And then for each one, I've got to find all of the leaves that are on one side of the split, meaning removing this edge as a cut. And then I want to make sure once I've found all the things on one side, I encode these 2 collections of things correctly as a binary string. So it's not that any one of those steps is particularly difficult, but what the question is really getting at is getting you to see that all of them are important as they come together. I think I've already forgotten the taxa here. I think is it person, man, woman, camera, TV? I think that was it. I don't know. Okay. But for this particular function, we're going to take a tree. We're going to form that matrix of 0s and 1s. And as I said, let's first identify the leaves, because every time I want to go through the edges, I want to not consider any edge that touches a leaf. So it's helpful to say, let's call tree.leaves. We have a method for that in datatypes.py, the definition of a tree class. And then we're going to build the matrix. The matrix is just a list of strings. So it's just going to be each string is a row. And then way down here, I'll eventually return it. I think I'll also be nice. I'm going to sort them first. Okay, so no reason not to do that. But the platform's not going to require that we do it that way. And once we've established what the leaves are, the next step would be to range over all the edges of the tree and find the internal ones. So I will say we're ranging over in tree.edges. And we could look at what the edges of the tree are going to be. There's no problem in refreshing our memory from data types. So the edges of a tree are going to come out as a list. And the first part of this makes sense. It's a tuple connecting two strings. So this is each node, each pair of nodes that the edge connects. And then we have a float that represents the edge weight. So fair enough. That's A, B, weight are what we're going to have. So we're going to range over that, and that means every time we range, I need to get the two nodes that I'm going to call A and B, but I also get an edge weight, and I don't need the edge weight to form the character table, so that's never going to be important. I'm just going to assign it with an underscore. The point becomes, I care about an edge if it connects to internal nodes, meaning A and B both aren't leaves. And so I can easily check that, fortunately, because I have a method for this. And I can just say, if it's not the case that in this tree, A is a leaf, and it's not the case that B is a leaf. In that particular case, we're going to say, all right, great. Find the leaves on one side of the tree. Okay, so this is the case that we're interested in. I will use a subroutine to do that. So I'm going to say side leaves is equal to the leaves on one side of the tree. So I need to know the tree, and I need to know the two nodes that form the edge here that I'm looking at. So A and B are the current nodes of this particular edge. And once I've set that, then I can say, well, there's some code here that's not, I'd say not technically necessary, since we're working with a tree that has this unrooted binary tree structure. But I'm going to be very precise, which is to make doubly sure. Let's say this again. Let's make sure that there are at least two leaves on either side. Okay, so what this tree is going to give me is it's just going to be a list of strings. And there's kind of two lists of strings that are relevant. There's the list of strings on one side and on the other. And leaves on side is just going to pick a side. There's nothing special about what the leaves are on, what are the taxa that are on one side of this edge versus the taxa that are on the other. But I'm going to say, I can know how big those leaf sets are because I'll say that the length of the side leaves is the number of leaves on one side. But I need to say, what's the other side? What is the other side's size? And it's the total number of leaves minus the length of the side leaves, because every leaf has to belong to one side of this split or the other. And then I want to make a check. So I want to say, if it's the case that one side size is greater than or equal to 2, and other side size is greater than or equal to 2. In this particular case, I'm going to say, we'll let, this is a good split of the data. I know that I found an internal edge, and I've got at least 2 things on either side, and that's good. If there's only one thing on one side, as I said, that's what we call a trivial split, trivial character, because in my evolutionary tree of me and everything, well, there's obviously going to be a split between me and everybody else in the tree, but that's not particularly useful. We need at least 2 things on either side. And so if it's a good split, then I want to rows.append something. So I'm going to say, let's add it to the table. So I will rows.append encode the split. We're just going to call a little subroutine here to convert this particular thing to ones and zeros. And I'll say for all of the leaves, but I need to know those because I need to know the order that's important. Remember that each row is in lexicographic order with respect to the leaves. So that has to be given. And then we also need to give it the side leaves because that's going to tell us these are the leaves on one side. Those are the ones that where the light is getting turned on. So this is just taking these 2 data pieces and converting them into a row, meaning a string of ones and zeros. And then we're in good shape. So at this point in time, we will sort the rows that we had and return them. And that sorting is just being nice to the user. Once I've made the character table, well, now I need to call, actually implement the 2 subroutines that we're looking at here. We have leaves on the side, and then we have the encode split. This is just a little bit of data formatting cleanup. This is a more interesting, I think, computational challenge. So let's look at that first. So we have a leaves on the side function that takes my tree as input. It takes a starting node as input. And the forbidden neighbor is a nice way of putting this. Basically, we have an edge connecting these 2 nodes. They're both strings. And we have a tree that they come from. And I want to reach everything from the start node that doesn't cross to node B, which I'm calling forbidden neighbor. So I'm going to explore from start in order to find all of those edges, but I'm never allowing myself to cross over to the forbidden neighbor. And there's a couple ways of doing that. One is I can constantly check to make sure that I'm not going across the forbidden neighbor. But the other way is to notice, well, if I'm at an edge, the only way of going to the forbidden neighbor is to go straight from the start. So what I will do is I'm going to apply a BFS, but I'm going to first create a visited set that will keep track of what are the nodes that I have seen. It's a set, of course, because I don't want duplicates here. And so it will start with start, but it's also going to contain forbidden neighbor in it too, to say, this is the clever approach that realizes, well, I'll just say that I've already consulted forbidden neighbor. I've already seen it. And so this means that I'm never going to allow myself to explore from it. Then so much of what we're going to do otherwise is, this is BFS. So it's similar to what we've done before with BFS, meaning I'm going to have a queue. It's a list of strings or nodes that I've seen. In this particular case, I don't want to add forbidden neighbor to it because that would allow me to explore, but I do want to add start to it. I'm going to maintain a head index, and I'm also going to maintain a collection of leaves that I've found, which also should be a set, and it should start off as something that's empty. There's also kind of a nice little first check to make sure that it's okay, because this is never going to happen in our code, but we should probably check if start is a leaf, because if when we go into the tree and we check that start is a leaf, well, we probably just add start to it, that collection of found leaves. But that's never going to be the case, because this wouldn't make any sense. If one of the nodes is a leaf, that's what we're trying to avoid in the first place. But this just generalizes our code just a little bit. What I'm really interested in is apply BFS. And so we'll have the same, I could copy this over, or I could just kind of retype it. We'll say While this head index that I have is less than the length of the queue. If that ever hits the length of the queue, then we know that we've kind of consulted everybody in the queue and we're finished. But we'll say node is equal to queue of head. So that's my current node. I'll add one to the current value of head to serve the next customer. Then we're going to range over tree.neighbors of node. Same thing that we did before. Remember that when we get the neighbors, each thing that we're going to get is an edge. And each edge that we're going to have is going to contain the node that we're connected to, but it's also going to represent, it's going to contain this edge weight, which I don't care about, okay, because we're just finding everything I can reach. I don't care about how much edge weight I'm going to accumulate on the path. And then for the current neighbor, I need to say, have I seen it? So if neighbor not in visited, and that's where our clever idea of making sure that, forbidden neighbor is not included here will prevent it from being considered because it is in visited. It's already in the set of nodes that I've seen. So I'm not going to allow myself to jump to it ever, but especially not in the first go. If it's not in the visited, well, here's where I'll say, let's add it to the visited set. So I'll call visited.add of neighbor. And then I'll say, all right, well, also, is it a leaf? Because if it's a leaf, that's good. If tree.isLeaf of the neighbor, I want to add it to found leaves. And then at the end of this process, I have visited it and I want to add it to the queue. So we're going to say queue.append neighbor. At the end of all of this, we're going to return the found leaves set, which hopefully will have some things in it. It will always have, hopefully it'll have some things in it. And that's it for our leaves on the side function. Of course, we have one more subroutine to write, which is encode the split. As I said, this is kind of our data cleanup, which says we've got a collection of leaves as a list of strings. And we have the set of strings, the set of nodes that are on one side, and we just want to encode this as a string. So this will say, create a string of zeros and ones where an element is 0 if it's on one side of the data, and it's 1 if it's on the other. And everybody in this set is going to get the same assignment. It doesn't matter. I could give them all zeros. I could give them all ones. It doesn't really matter. How I'm going to do this is to say, let's grab the first leaf and see if it's in this side. Okay. So I'll say that the first leaf then is equal to, let's look at the sorted leaves of 0. And I'm going to have a Boolean value or variable called first leaf on this side that's equal to, let's look at that first leaf. And this is going to be a really funny way of saying it, but let's say first leaf, is it in this side? So it's going to check to see if first leaf is an element of this set of strings. And if it is, this is going to return true. If not, this is going to be a false value assigned to that variable. And then let's create the list and range over leaves and assign. So I'm going to create a list of characters. It's going to start off empty. Eventually, I'm going to return the join of them with an empty string. So that will return a string here, which is what we want. And then I'm going to also say, let's range over the leaves. So for leaf in sorted leaves, I will say, the same thing. The current leaf on this side is equal to a Boolean value to say, is this leaf in this side? And if that's the case, so if this is true, well, I need to decide on giving it a value of 1 or not. So if this is equal to whatever this first leaf's value was, it means it's on the same side as the first leaf. And I'm going to chars.append something. I could do a 0. I could do a 1. I could do airplane. I mean, that's going to be kind of annoying to the user, but it doesn't matter. And I'm just going to set it to 0. Otherwise, I'm going to chars.append 1. And I think we should be in good shape then. So let's see what happens. Python 3, this is CTBL.py. None type is not iterable. That's not fun. That's not fun. So line 123. I like this is 2 lines anyway. Okay. Yeah, little minor Python thing. When I sort it, yeah, it wants me to sort it first and then return the rows. Okay. Anyway, here's what I obtained. That looks awfully similar to what we saw on the platform before. So that's good. I've already solved the preceding problems, I think. So I'm just refreshing the page here. Oh no. Well, this is our solution. I've got our, this is KMP, isn't it? Oh, mercy. Okay. So we had this KMP problem that I had never cleaned up. And I guess it's a prereq for this. Uh-oh. So I need to solve KMP here shortly. I actually have, I believe I have I have a solution to KMP. So what I will do is I will go back and solve this at some point in time. I know that I have some code written for it already. So I'm just going to make sure, just so that we can actually proceed, I will make sure that I can solve it. Nope. Okay, good. So let me make sure that this is giving me something. So it's waiting on me to solve it. It's returning something. That's good. So we'll explain this problem at a later time. But for now, I am going to solve it just so that I can move on. It's a necessary prereq for what we're doing. It's actually a very short function, and I would just explain it live, but the point of it is, this is one of these problems where the explanation is like 30 minutes long and highly non-trivial. So I have the function here. You can take a look at the code, but actually explaining it is not a fun one. So we're going to come back to that. And even with an optimized algorithm, it's a big data set that we were given. So this is one really long string. So it's taking some time. Sit tight. I hope it finishes in time. We have 2 minutes and 49 seconds. My aside here is The KMP algorithm is kind of, I don't know. I feel like it's pretty overrated. Sorry to Donald Knuth on that. But the reason why is a very straightforward algorithm for this problem would actually also be pretty fast on small data. So we kind of built in, for producing this failure array, we built in larger data sets so that you really had to implement the faster approach. And I guess there's ways around that. You could just use a faster language. But this is the frustration of using Python. So at this point, I'm just kind of praying it finishes in a minute and 30 seconds. It will, I think. Otherwise, I'll just convert my code to a real language and we'll have it running that. Oh, this is the slow implementation. That's our issue. Okay. See if I can fix that. Let me see. Yeah, I remember now. We implemented this. And then my entire point was this is a very natural implementation of creating this failure array, which is inherent to KMP. But the natural way of making it is just really slow. So I'm going to need to rerun this so that I don't have to get into just big O of n and big O of n squared. So I've got a little bit of faster code here. Yeah, we'll explain this at a later time. Break it. Yeah, so see how much faster that is. Let's see if I've run out of time or not. I hope not. Oh, I didn't get it in. All right, well, this will be very fast. This will be very fast. So that's a teaser for me explaining at a later time a rapid rapid algorithm for producing this failure array. But for now, we're going to get a correct answer, I hope. Okay. And we can go back to creating a character table, which is the problem that I actually wanted to care about. Okay. So we're back. And now I can download a data set for character-based phylogeny. It's going to produce this character table. And I'm going to make sure our old data set is gone. Call that dataset.txt. And run it this time. And what I need to do also is one more thing. Make sure that our parsing code isn't commented out. And now the output is going to contain our answer, I hope. I hope. And there we go. Okay. A little bit of a detour, but we're back on the track. Now we've unlocked 3 more questions. One is going to be really short, one a little bit longer, and one kind of medium. Next one we're going to look at is CSTR. Thank you for your patience there. All right. CSTR is creating a character table from genetic strings. And what do we mean by character table? Well, we mean this table of ones and zeros where each row represents ones placing all of the taxa in our tree on one side of the tree, and 0 represents placing them on the other side of the tree. So in a previous problem, we talked about this means that there's some edge in the tree that if you remove it, everybody with a 1 goes to one side of the tree, and everybody with a 0 is on the other side of the tree. So it separates it into 2 separate trees. This concept of a split is really useful because it's the classic way in which we would draw evolutionary trees. We would form the splits first. And then once we've got something like this character table representing the splits, then we want to take that and produce a tree. So what we did in CTBL was a little bit backwards. It was saying, here's a tree, infer the character table from it. But what we actually want to do is go in the reverse direction. And this problem is preparing us for that, which is I want to have the splits, regardless of whether they come from dinosaur fossils or they come from genetic data. And then from those splits, from this character table, I want to then form the tree. This problem is doing the first part of this, which is forming a character table not from the tree itself, but from some raw data. And these days, we're not looking so much at dinosaur fossils. What we're looking at is something like a multiple alignment of a bunch of genes. So our input is going to be a collection of DNA strings, in principle corresponding to like, for example, a multiple alignment of genes. And a real multiple alignment would have some gap symbols in there too, but we can look at that in a separate problem. What we want to produce is a character table, one for each interesting column of the data. And how is it that I define an interesting column? Well, remember that a split that's not particularly useful is like, oh, I'm on one side of the tree and every other living thing is on the other side of the tree. Yes, we already know that. So that would be what we call a trivial character. We want non-trivial characters that divide, more than one thing to one side and everybody else to the other. And if you look at this particular multiple alignment, you'll see like the final column, this doesn't tell me any information. Everybody's a C. So this is completely non-informative, other than saying that everybody has a C at that location. But from the perspective of trying to form an evolutionary tree, this particular column is useless. There are a lot of other useless columns too, like this second to last column contains a T in the last row and a C everywhere else. This is analogous to me saying, well, yeah, I know that this organism is eventually going to be different from everybody, but this separates me from everybody else in the tree. The same thing happens here, where you have one lone C and a bunch of A's. It happens here with one lone G and a bunch of T's. It happens here with one lone T and a bunch of C's, and it happens here too. So you might say, are there any interesting columns? And we constructed this data set to point this out as a sample to say, yes, the first 2 columns are interesting because you have 2 C's and you have 3 A's in the first column, and in the second column you have 3 G's and 2 T's. So in each of those cases, that's a column that we want to look at as a potential way that we could divide the data into these splits. And in the first case, where you have AC, AAC, you're going to notice that gives us 1, 0, 1, 1, 0. So we arbitrarily assign A to 1 and C to 0. But if we have a column that has only 2 symbols and it divides the taxa into 2 collections that have at least 2 things in them, then that becomes a non-trivial split. And we can say whether we assign the A's to 1s or A's to 0s, we're going to get this row. Similarly, the second column, which is the next non-trivial split, is 1, 0, 1, 0, 0. Why do we get that? Because, well, the G's now correspond to our zeros, and they could correspond to 1s, but in this particular case, we're going to get 1, 0, 1, 0, 0. So that is the note, that this character table doesn't encode these trivial characters. So you might wonder, well, why is it the case that this multiple alignment has 8 columns, but there's only 2 rows of this? It's because there's only 2 columns that are of particular interest in this sample data. This leads us to the question here, which is, of course, the input is going to be a collection of strings, and the output is going to be that character table that we infer from it. Once we have that, then we can say, oh, now I've got the splits, and as long as I have a method to take that character table and form an evolutionary tree, I'm one step away from actually making a tree from my data, and we'll encounter that soon. So coming back to the code, our idea is to range over the columns of the data, okay? If every symbol in the column is the same, or there's only one symbol that's different, I'm not going to consider it. And I think I'm going to only look at columns that have exactly 2 different symbols in them. So a lot of this problem is going to be just part and parcel of like processing the data and making sure that every column, if I'm looking at a current column, that it falls in the right bucket. But once it does, then it's going to be pretty easy. I just make a row corresponding to that column. So I say range down the column and say, do you see one symbol or the other? And one symbol is going to be a 1 and the other symbol is going to be a 0, and append it as I go to this growing character table. So I can do this with, hopefully not that much code. I'm going to just try and pack it all into one function here, which is to take my collection of strings, that's my multiple alignment, and then make this character table that can be inferred from it. And, the first thing I might do is, make some checks. So if it's the case that length of the strings is equal to 0, that would be bad. So I'd return an empty list. Next, I probably want to know some things about the data. So next, get the number of columns and make the matrix. I'm going to make a strong assumption here, which is that the data I'm going to get all the rows of the multiple alignment are the same length. So I could have an assertion function to do that. In this particular case, I'm just going to assume that the data that come from the Rosalind platform are okay. So we'll say that the string length is equal to the length of strings of 0. We should assert all strings have this length, but that's okay. And I'm going to make my rows, as I've done before, to be a list of strings that starts off being empty. And eventually I'll return those rows. In the meantime, I want to range over the columns and grab the current column. So as I go through the multiple alignment, I'm looking one column at a time, and then I'm going to consult the current column to see what's interesting here. So I will say for k in range over the string length. K is representing the column index that I'm currently interested in, and I need to make that column. So column is a list of strings. It starts off as empty, and then I'll range over all the strings, and I want to append to that column s of k. So once I've done that, I have a blank column that I have. Then I want to say, what are the distinct symbols occurring in that column? And we could range through and make a dictionary or something like that. Far easier to just say, well, set of column is built in. So if I have a string and you call set on it, that's going to give me all of the symbols that are distinct in it. So I'm going to call that function and call the resulting character set distinct symbols. And now we want to perform some checks. So ensure that the column has at least 2 symbols. So if the length of distinct symbols is equal to 2, so that's where we're going to say We're interested in things that truly divide the data into exactly 2 pieces. If they divided them into 3, like we saw an A, a C, and a T, that's just going to be a trickier column to work with. So in this formulation of the problem, we're going to say if you have exactly 2 symbols, that's good. That means that this divides the data into 2 equally sized, or not necessarily equally sized, but 2 pieces. And then we're going to say, all right, well, let's count the number of appearances of each of the 2 symbols, because we want to ensure what? That, each symbol occurs at least twice in that column. Otherwise, we're not going to consider this as a character of interest. So I'll say our reference is just going to be the first symbol. So that's the first symbol in the column. And let's count how many times it occurs. So I'm going to say count of reference is equal to, and here's where I'm going to have, in this particular case, I'm going to say, let's use column. So if you have a string, there is a method here called count that we can just call. I don't want to, I usually write our own code for everything. There's no reason to not call this. So I'm going to count the number of occurrences of the reference symbol. Or I could call that first symbol. And so that tells me how many times I see it. And now I'll say count of all the other symbol. So we have 2 symbols here. How many does each occur? Well, this is now the length of the column. So the total number of symbols minus the number of times that we saw the reference symbol. And everything is okay if the count of reference is at least 2 and the count of other is at least 2. If both of those things are true, then we're good. This is a valid character that we want to use, and make a row for it. So we'll say characters is a list of strings that starts off as empty. Eventually we're going to rows.append the join with an empty string of the characters. In the meantime, what I want to do is, range over the column and assign everybody a 1 or 0. So I'll say for each character C in the column. Once I do that, I'll check to say, is it the case that C is equal to the reference? So is it equal to the first symbol that we saw? I don't care what the first symbol was. It could be, the majority or not. The problem doesn't actually check that I care about the majority. So instead what we're going to say is, if it's equal to the reference symbol, chars.append something. Could be an X, could be a 0, could be a 1, doesn't matter. We're producing binary data here, so this could be a 1 or a 0. The order doesn't matter, the autograder won't care. But whichever one I pick, if it's not the reference symbol, it should get the other value. This way the data are dividing into the 2 pieces that I care about. And then that's the end of the function, because I'm going to append that particular row to the growing collection of rows. And at the end, that's what I'm going to return. So I should be able then to run this. And I believe we see the same thing that we saw on the platform, which looks good. So we can now download our data set and call it data set in our file explorer. Comment out, uncomment out, always use the wrong term. Our parsing part of the code. And then the answer goes to output, which I'm just going to copy in and place in the platform. And we get a correct answer. All right. Karen, welcome from Boston. Thanks for joining us. We got 2 more questions today. One a little bit longer, one seemingly very hard, but actually not. We're going to use a little bit of math. QRT is going to be next. Just going to get set up for it. QRT is called quartets. And the idea of this question is as much to familiarize yourself with some of the terminology of evolutionary tree construction as anything else. And in a classic formulation, we have these splits, these ways of dividing the data into two parts, and we might want to make a tree from those. That's all well and good, but it makes these strong assumptions, as we have seen. So, for example, if we're looking at a column of a multiple alignment, then we've needed to assume to get these binary characters that everybody has one of only two different letters. And if you have 3 letters or 4 or 6 different options in the case of amino acids in this column, it's not clear how that divides the data into 2 pieces. For a classic case, there also might be some data that you're just missing. So there might be, if you want to look at a particular leg bone of a dinosaur, it might be that no one's ever found the leg bone from that dinosaur before. And so there are certain attributes that you don't possess for every single organism. If we think about that on the level of a character table, then that means that the character table could have these X's associated with it, where what this is saying is we don't have data that we trust, at least, corresponding to the elephant for this first character, but we do have that it's a 1 in each of the remaining 2 rows. So the character table contains 1s, 0s, and then special values to indicate that we don't have a value for that particular character. Then the question becomes, what do we do? Because, well, there's not a split really associated here. And we could take all the 1s and 0s, but what we want to do is kind of generalize what we're saying here to say the split assumes that we have all of the taxa involved in the split. So everybody goes either to one side or the other. But now we have this kind of third hazy option. And another classic way of making evolutionary trees is to make evolutionary trees from what we call quartets. So we think of a quartet as a specific version of what we call a partial split. What do we mean by a partial split? It means, well, there's 2 disjoint subsets, A and B. So they contain completely disjoint sets of taxa, but they don't necessarily contain everybody in the set. What this is saying is, if you want to use a very set theoretic notation, it's not required that the intersection of A and B constitutes the entire set. The complement of that intersection is just the taxa that would correspond to an X. We don't have conclusive evidence for that particular character. And a quartet is a specific example of one of these partial splits, where the 2 collections of things A and B each contain exactly 2 elements. So the idea is you might have 100 taxa. The quartet is only going to represent a connection between 4 things. And all the quartet is saying is that A and B belong to one side of the tree and C and D belong to the other. In theory, if I generate enough quartets for enough pairs of taxa, I could still produce the evolutionary tree from these things, because I would have enough. It's almost like a big logic puzzle. I'm able to say, well, these 2 organisms are always on this side of the tree and this side of the tree, and give me another 4, and then I'm going to continually rule processes out. So the algorithms are doing a fancier version of that if you give them a collection of quartets. But the idea here is, again, if you have partial data, your splits might not be perfect, but you're still going to be able to produce an evolutionary tree if you have enough of these relationships like this that say elephant and dog belong to one side, rabbit and robot are on the other. Well, what about cat and dog? We can conclude that they're closer to each other than mouse and rabbit. Mouse and rabbit are closer to each other than they are to cat or elephant, and so forth. So this is still giving you good information. And what the problem is asking you to do is to say, well, if here are our taxa, and here is this partial character table, what can you actually infer from this character table where each row corresponds to a character in terms of quartets? If you look at this particular row, it doesn't give you anything interesting, because it says dog is different from cat, rabbit, and robot. So each of the elements here corresponds to a column here. But we know this is the same example that we had previously in a previous problem about a trivial character. I am obviously different from everybody else in the tree, but that is not informative. So nothing about this initial row is useful. But the second row is useful, because the second row tells us that dog and elephant are closer to each other, because they share one of these characters than they are to either rabbit or robot. So that's what we see here as one of our quartets. Finally, we look at the third row, and you'll notice you have 3 ones here and 2 zeros. So what this means is, well, on one side, you have mouse and rabbit. You'll notice mouse and rabbit occur 3 separate times here. So it's saying mouse and rabbit are closer to each other than they are to any pair of organisms that we see here. So we could have cat and dog. That's what we have there. We could have dog and elephant, which is what we see here. Or we could have cat and elephant, which is what we see in this case. So every way of pairing 2 things from this list of 3 things represents a quartet. Similarly, if we had 4 zeros in this row, well, we would take all pairs of those. So the very fancy term of what we're doing is forming a cross product. So we have all possible pairs of elements corresponding to 0, all possible pairs of elements corresponding to 1, and we take all pairs of the pairs. And we use that process to form the quartets that we see. The idea of our algorithm is to range over all these rows, identify if that row gives us any particular information that we care about, in that it needs to have at least 2 zeros and at least 2 ones. If it does have at least 2 zeros and at least 2 ones, take all the pairs of taxa corresponding to a 0, all the pairs that correspond to 1s, and represent all pairs of pairs. So we're ready to code this. I will point out one other thing, which is that it makes sense to establish a little alias for me, and I put this in datatypes.py, to establish what is a quartet. And this is a 1-line alias that says a quartet is a tuple of 2 things. So it is a pair of 2 things that are close to each other, another pair of things that are closer to each other than anything from the other pair. And so if we want to represent those 2 pairs, we need a pair to do it. So it's a pair of pairs or a tuple of tuples. Now that I understand that, I will just use the term quartet to refer to a pair of pairs. So 4 things, I have an A and a B that are close, and a C and a D that are close, and the quartet is the join of those 2 things together. Now I can come back to qrt.py and actually write my problem. So the function that I want to produce is called quartets from table. So I have a list of strings corresponding to my taxa. These are my leaf nodes. And I have the rows of the character table. So I'm just going to form this as a list of binary strings. And then I want to form a set of quartets. So why is it a set? Well, I could, in theory, have multiple rows describing the same quartet. And I don't want to duplicate them because if I say cat and dog and elephant and robot, I don't want to have 14 copies of that. There's no reason for it. So the first thing I want to do is make our set. So it's a set of quartets. So quartets is a set of quartets. And it starts off as empty. Not as set P, but as an empty set. And now I said our idea was to range over all the rows. And then for each row, we're going to take all the pairs of 0 to 1 taxa and add them if we haven't already seen them. So the first thing we're going to do then is to say for row in the character rows. And then for a particular row, we're going to say, all right, well, for this particular row, I'm going to call a subroutine called sides for character. And that's going to give me like 2 lists again. So if we look at sides for character, I already have the signature here. It's going to take a list of strings corresponding to the taxa. It's going to take the current row that I'm looking at. And then it's going to split, what are the taxa on this side and this side. So this is like cat, dog, and elephant, and this is like rodent, rabbit, and robot. Okay, so it gives me the two sides of the character row. So I'm going to let that happen as a subroutine. The 2 things I want to give it are, as we saw, we give it the taxa and we give it the current row. Once we obtain that, it's going to give me 2 things. It's going to give me all the things on one side, all the text on one side, all the text on the other side. So these are the ones that correspond like a 0. These are the ones that correspond to a 1. Remember, there are some that might have other values like an x. We're just going to ignore those. If it's the case, we only want to do this if side A and side B, so these are the 0s and the 1s, if they have enough elements. So they need to have at least 2 each. So if length of side A is less than 2 or length of side B is less than 2, I'm going to use a continue statement to say carry on to the next row. I also could do it the other way, where I make sure that the length of side A is at least 2 and the length of side B is at least 2, and then I enter an if block and only continue if I only execute the if block if that's true. That would work too. That's going to make what's already a very nested collection of code extremely nested. And so instead what I'll say is, let's range over the elements with one value and form all pairs. So for I in the range over the length of side A, this may have 2 things in it, it might have a million things in it. And now I'm going to range over the elements with the other value. Okay. So that will happen later, but to form all pairs, I'm going to range over length of side A, and I'm going to range over length of side A again, except I only want to form each pair once. So, and this will form pairs of objects with themselves. So this isn't right. What I instead want to do is, and this is similar to what we've done before when we worked with distance matrices, I'm only looking for unique pairs, which means I'm going to start my ranging at I plus 1. So I'm going to start with the current element's neighbor to the right and only consider elements on that side. Once I've got that, I'm going to say A1 is equal to side A of I, and A2 is equal to side A of J. So this is my current pair of elements, A1 and A2. Then, after we have these 2 elements, that's our first pair. But then I want to range over the elements with the other value from the other side. So I'm going to have, and this is why I used a continue statement earlier, I'm going to have so much nesting because I need a 4K in range over the length of side B. And then I'm going to have a 4L in range over the length of side B again, but I'm going to apply the same trick. So this is going to be K plus 1 to length of side B. And then I'm going to have a B1 equal to something, and that something is side B of K. And then a B2 is something, which is a side B of L. And then after all of this, now I'm ready to say, add this to our quartets. So we will say quartets.add to my set. And it's tempting to go, well, it's A1, A2, so it needs to be a quartet, which means it's a pair, B1 and B2. And this is going to be hideous because I need to put it in yet another collection of parentheses. But that's a tuple of 2 tuples, which is this. Yuck. But actually there's another problem here, which is I might have added things in such a way that still has duplicates. So it might be the case, and you wonder, well, no, because A2 has to be bigger than A1, J has to be bigger than I, and L has to be bigger than K. But remember, there's multiple rows that are involved here. And so for that reason, it might be the case that for one quartet, we have A and B inside A, and for another quartet, they're inside B. And so I might add cat and dog, and then robot and elephant, but then add robot and elephant, and then add cat and dog. And that's the same quartet. So there's a very minor point here, which is that I want to only add them if I really haven't seen this before, which means I'm going to use a subroutine called canonical quartet that takes these 4 elements and tries to add, say, there's only one way of representing these things, which are this is the smallest, this is next smallest, this is next smallest, and this is next smallest lexicographically. So even if they've been scrambled somehow, and I had, what did I have? Cat, dog, elephant, and robot. I'm going to demand that cat is less than dog and elephant is less than robot, and this thing is less than this. So as a result, that's going to make sure that I'm only adding each quartet exactly once. So I'll have to write that subroutine, but the point is, in the meantime, once I'm finally done with this, I'm going to return my quartets, because that's what I care about. And that's our highest level function. Of course, we have two subroutines to write. We've got to write sides for character. So this takes a row of my character table, and it takes the names of the taxa so that I know the order of the elements in that row. And then it just says, go through and find zeros and ones. So that's all it's ultimately going to do. So we have a list of strings, which are our taxa. We have the row that I'm interested in. One is going to put a taxon on one side. A zero puts that on the other side. Literally any other character is going to be excluded. So for this function, I'm going to make my side A as a list of strings. That's what's going to get returned here. And then we're going to return this. So I'm returning two lists. So I'm going to call those side A and side B, which is what we called them previously. And then eventually I'm going to return them. In the meantime, what I want to do is, range over all the taxa and identify which have value 1 versus other. Ignore. So for I in range over length of the taxa, this will range over the row. We assume that the length of the taxa is equal to the length of the row. That would probably be an important thing to assert, but we're assuming that the data have this nice form for us. So the current symbol is row of I, and don't need a colon after that, but the current symbol is row of I, and then I'm going to say check it. Is that symbol equal to 1? And if so, side A dot append of taxa of I, and otherwise, else if symbol is equal to 0, we're going to side B dot append taxa of I. And it doesn't matter whether you have a 1 here, you could have a 0 here. Yeah. As long as that's a 0 and that's a 1, doesn't matter. I'll take it back to that being a 0 and that being a 1, because we just want to ignore anything if there's an else. So any other symbol, we just don't take action. And that's all this function really does. It just ranges over and finds zeros and ones. Finally, we have our canonical quartet. So it takes a bunch of strings, and then it produces a quartet of them. The idea is A1 and A2 are a pair, and B1 and B2 are a pair, but the canonical quartet is going to assume for us that whatever we return has the smaller, the first in terms of lexicographic order, the first of the two elements is going to occur first for this pair and for this pair. And then we'll make sure that the first pair is also occurs before the other pair in the dictionary too. We're going to have a nice built-in operation for that. So kind of in old school programming, this would be a very annoying function to have to write. But fortunately, we have, thank you to Python for having a lot of functionality with the less than operator. So I'm going to say, if it's the case that A1 is less than A2, that's good. Pair A is going to be A1, A2. Else, its pair A is going to be equal to A2, A1. And we eventually want to say, we're going to return pair A, pair B, but we want to be careful, and I'll say that here momentarily, but do the same for pair B. So we're going to say if B1 is less than B2, pair B is equal to B1, B2, else pair B is equal to B2, B1. And really, a lot of languages would be angry at this, but Python's so loosey-goosey with scope that this is all right. We're going to be able to access it even though this is declared inside of an if statement. And it's tempting to just return pair A, pair B, but this is where, we need to be careful that we know that in each pair that we have the smaller element, but they also could be switched. So we want to ensure that we don't add, I don't know, A1, A2, or let's say XY, WZ, and WZ, XY. That would be considered a duplicate, and this doesn't handle that. So what I want to say is, for the canonical one, we want to assume that like the first element here is smaller than the first element here. And if there's a tie, that the next element is smaller. And that would be annoying to check. But fortunately, again, thank you to Python, we have if pair A is less than pair B. That's going to give us that function that we care about. I'm going to return pair A, pair B, and else I'm going to return the switch of them. So I ensure that the first pair is lexicographically smaller. And that's pretty cool. That's both of our subroutines written. So I should be able to run this on our sample. And this appears to match, I think, what we have here. So this is a slightly different data set, but you know, we're going to see we do get a bunch of quartets here. So let's comment out this, go to our platform, download a data set, put it in our file explorer as dataset.txt. And run this one more time. And it's cool because, I mean, this is, we actually have real species names here, which is cool. I'm going to go to the output. Here's all the quartets we can infer from it. And then in theory, we could just now write an algorithm that takes all those quartets and builds a tree out of them. But for now, we're just interested in the quartets themselves. We can infer them from the data, and we're good to go. One more question today, then we're going to call it a day. Our question's going to be CUNR, I believe. So this is going to be a shorter question and a little bit more of a mathy one. So it won't be too long. Won't be too long. All right. CUNR is counting unrooted binary trees. This problem takes us back to counting. So we've counted a lot of things in our Rosalind challenges. What we're currently going to count is the number of unrooted binary trees. So these are trees that have a specific property, which is that you have leaves which have degree 1, but every other node is going to have degree, meaning number of edges incident to it, equal to 3. So there's a natural combinatorial question here, which is to say, okay, how is it that this number of unrooted binary trees, which you might call B of n, where you're fixing the number of leaves, how is it that that grows? Is there a formula that we can find? The assumption here is that the leaves themselves are labeled. So the leaves are labeled like cat, dog, robot, elephant, person, woman, man, camera, TV. And then the internal nodes, they're flexible. So we could write this out by hand, and the classic way of counting something would be enumerate everything that you find by hand, see if you can form a conjecture, see if you can prove it. Computers have greatly empowered, turbocharged this way of solving things, but this is a classic question, which is we're going to give you an integer n, and we want you to give us b of n. And the Rosalind trick is this number is going to grow very fast. That's the hint. So we're going to take the remainder when we divide by 1,000,000. But our idea is, I will give you that for free, that these are all the unrooted binary trees with 5 labeled leaves. And I've colored them in case you can't quite see them. But the idea here is blue and red are neighbors here, but green and red are neighbors here. And green and red are also neighbors here, but you see this is a different tree to number 2 because the orange node is on its own over here, but in here the purple node is on its own. So it's still a different tree. This seems like a very intimidating question, which is how many of these things are there? I don't know, if I give you 100 as the number of leaves. And what this problem is really trying to give you, to show you, is we can answer a pretty complicated question involving a formula that's going to be absolutely enormous by placing this on some firm mathematical footing. In this particular case, we're covering this problem right after talking about splits, because the way to figure out how to count this number of trees is inherently related to the concept of a split or an internal edge. Because say, for example, that I was going to try to figure out the number of binary unrooted trees with 6 labeled leaves. So I have another color, I don't know, it's yellow or something, that I'm assigning to some additional node that's going to fly in, and it needs to be inserted somewhere to form a tree. And the idea is all these trees are distinct, and I could form a tree with my 6th leaf if I place it somewhere in the trees. In particular, if I place my leaf at any of these edges and connect it in, so I want you to imagine that I connect it here, meaning I and my new yellow node are going to be neighbors. That's different from the tree than if I place it here. And I could place the yellow node here in this tree, of course, because these two trees are different. The 2 resulting trees where I place the yellow node here in the larger tree, those are going to be different too. So as a result, in each tree, I get a different tree if I place it on any of the possible edges and sort of extend my new node in. What this has given us is like a pretty idea, if only it were a formula. And the fortunate thing is what we've produced very much is a formula. What we've said is that the number of trees, if I have n plus 1 leaves, is equal to the number with n leaves. So b of n plus 1 is equal to b of n times the number of edges that we see in any of these trees. And the problem with that is, well, we can write that down. That's all well and good. We can write down that particular formula as b of n plus 1 is equal to b of n times the number of, I'll put it in parentheses, the number of edges in an unrooted binary tree with n leaves. Because those are all the attachment points for leaf n plus 1. That only works if this is a fixed quantity. So if this varies, like every unrooted binary tree has a different number of edges, well, then this formula becomes a lot trickier because we don't get this multiplication for free. It turns out that this number of edges very much is invariant. We've already seen 2 problems in this series that were really helpful. In the problem with ID tree, T-R-E-E, we learned about this invariant property of trees, that if a tree has m nodes, then it always has m minus 1 edges. It has 1 fewer edge than it does number of nodes, regardless of what the size or shape. We also went further, though. So we've already seen a problem, it was INOD, where we worked out that, well, this question, we talked about the handshake lemma, and we said if you sum up the degrees of all the nodes, that always equals twice the number of edges, because it's like going into a party and you say people shake hands, and then you ask each person to all the people to add up the number of hands that they shook. well, that's always 2 times the number, that sum is always 2 times the number of handshakes. So this idea extended to the network, and we used it with a little bit of algebra to say that the number of internal nodes of a tree with n leaves is equal to n minus 2. This problem is going to put those two ideas together because, well, we know that the number of edges is equal to the number of nodes minus 1. And we know that for this specific type of tree, which is an unrooted binary tree, the number of internal nodes is equal to the number of leaves minus 2. So we put those two things together and say, well, the number of internal nodes is equal to n minus 2. And the number of edges, then, is equal to, in a UBT with n leaves, is equal to n plus n minus 2 minus 1, which is just 2n minus 3. Okay, so we put those two facts together, and we get this property. That's useful because now this formula, this 2n minus 3, simply goes in here. So this just becomes that b of n plus 1 is equal to b of n times 2n minus 3. And that's good. The only issue becomes, well, that's a recurrence relation. But how does it lead to a formula? Because I could start with b of 1 and then compute b of 2 and then b of 3 and so forth. But it would be so much nicer if I just had one formula for b of n. Note, though, that what this is saying is the number of unrooted binary trees with n plus 1 things is equal to the previous computation times this thing. So I also could say, like, in turn, the other way of saying this would be, what is b of n? Well, b of n then is going to be b of n minus 1 times, and in this particular case, it would be 2n minus 3. In this case, because n is one small, the input's one smaller, this is going to be 2 times n minus 1 minus 3. Or b of n minus 1 times 2n minus 5. When we expand that, we get 2n minus 2 minus 3, which is 2n minus 5. So when you put these two things together, and you could do the same thing, b of n minus 1 is equal to b of n minus 2 times 2 times n minus 2 minus 3, or b of n minus 2 times 2n minus 5, 7. So you get a chain. So b of n plus 1 is equal to this, but now b of n is equal to this, and b of n minus 1 is equal to this. So what we see is, at the end of this, we get b of n plus 1 is equal to 2n minus 3 times b of n, but b of n is equal to this thing, so I'm going to say that, well, that's equal to 2n, probably should have a comment. So this is 2n minus 3 times, what is b of n? It's 2n minus 5 times b of n minus 1. What is b of n minus 1? It's equal to 2n minus 3 times 2n minus 5. And we said b of n minus 1 is equal to this expression, so it's times 2n minus 7 times b of n minus 2. And we can't help but notice a pattern. And that's what all of mathematics is noticing a pattern and applying some techniques in order to represent that pattern in some formalized way. So in this particular case, we get that it's 2n minus 3 times 2n minus 5 times, and we keep forming this chain. So it's going to be times 2n minus 9, and so forth, until, notice, all of these numbers are odd, because this number is even and we're subtracting an odd number from it. So as you keep multiplying down, eventually you're going to have times 7 times 5 times 3 times 1. This is called a double factorial, and it's often written such as a product of odd numbers. all the way down to 1, and it's often written as 2n minus 3 double factorial. We're interested not, I guess, technically in b of n plus 1, right? We're interested in b of n itself. That's what the problem asks us for. But notice, well, b of n we computed here as 2n minus 5 times b of n minus 1. So we're just losing this 2n minus 3 term. And so b of n is 2n minus 5 double factorial. And that's what we care about. So this is the answer. Is this. That makes actually solving this problem computationally very straightforward. So we know we just want to compute 2n minus 5 times 2n minus 7 times 2n minus 9 and so forth. And we want to take the modulus each time. So we take an input as n, and we also take a modulus, which also might be none. So that allows us to actually compute the exact number without the modulus. But for this particular problem, we're going to set the total equal to 1. Eventually, we're going to return that. And then in the meantime, the only thing that we do is range over all the values that we care about. Now, this is tempting to go down to, the question is, where does the range start? And the range needs to start where the number of unrooted binary trees starts. So if we think about this, the last thing we want to do is do this, 1 to n plus 1. So that would be like, oh yeah, we're ranging from 1 to n, that's good. And then the current factor that we care about is 2 times k minus 5. And what I want to say is that the total is equal to, normally we would just be total times equal to the factor, but remember we've got to take the modulus every time we go through. So we're going to say the total is equal to total times the factor. And then after I have that product, we're going to modulate by the mod. And if that's none, then this doesn't do anything and we're in great shape. The problem becomes, well, what happens if k is equal to 1? This is -3, and -3 multiplied by our expression is not going to be good. Where we want to start this is where this becomes 1. And this becomes 1 when k is equal to 3, because then that's 2 times 3 minus 5, which is 1. And that makes a whole lot of sense because, well, what's the smallest unrooted binary tree? It's not x to y. And the reason, well, I guess that's the number of unrooted binary trees with 2 elements in it. But the smallest one that we want to have is, where you go x to z and, or some blank thing, and y connects into it. But then this connects into some z. So that's really the smallest unrooted binary tree of interest because you have 3 leaves and you have 1 internal node. So as a result, you want to start your counting process to say b of 3 is equal to 1. And so we want to go down to b of 3. And we know b of 3 is just going to be 2 times 3 minus 5, which is 1. So at the end of the day, this is good. Our ranging works now. We're not going to be picking up any negative numbers. And we can save that and run it on our sample. And for the sample that we have, okay, that might not be particularly interesting. Let's give it at least something like a 7. We're going to see that's a product, 945, okay, which is going to be 2 times 7 minus 5, which is 9 times 7 times 5 times 3. Hopefully that gives us 945. Let's see. We can get data set. 5 should give us 15. So 5 gives us 15. 6 would give us 15 times 2n minus 5, which is 7. So that's 105, 7 times 15. And then when we go to 7, multiplying that by 9, which gets us to 945. Looks pretty good. The only other thing we should do, add our data set. And make sure that we're running the parsing part of our code. Run it again. Here's our answer, modulo 100, or 1 million. So our data set is 870. That is going to be an absolutely gigantic number of trees. And so as a result, we're just modding by 1,000,000 each time. So we wind up with what seems like a much smaller number. But the actual number of trees is going to be far more than the number of atoms in the universe. Okay. And we got the problem right. 6 problems solved today, all coming at evolutionary tree construction from related but different angles. We've done a lot. We implemented breadth first search like 3 separate times. 2 times were very similar, but we've seen how important that can be for traversing trees and finding paths. Anytime you want to find a path connecting a node to other nodes or every other node in a tree, breadth first search is always going to be your friend. We learned that. And we've created a foundation for ourselves to start actually building evolutionary trees from data that we might have. So that's what all of this is leading up to, that we worked with character tables. We looked at Newick format. We worked with having a multiple alignment and trying to identify the splits in that data, because the platform is leading us to be able to say, once I've got those splits or I have the quartets, let's make the evolutionary tree that corresponds to those. And that's where we're going to have kind of the more final boss of evolutionary tree construction. That, of course, is going to be for a later time. We've done plenty today. I'll plan on seeing you next time, where we're going to take the next steps. And we're getting pretty good. We're getting pretty advanced. As always, like and subscribe. Check out all of our other platforms. If you want to see more about evolutionary tree construction, we have an entire chapter on it in our bioinformatics algorithms textbook. So we dig deeply into that. That has print and ebook formats where you can implement all kinds of your own algorithms and get automated credit for them. But that's it for today. I can't wait to have you next time. Thank you for joining us, and we'll see you soon.